Hi, so I'm Brian. I'm the head software engineer for the feature store at Doordash, and today I'm here to talk to you about our journey from moving to a single service that pipelines features to a single node on Redis, to a cluster, to a fleet of Redis clusters and Cockroach DB service, including an all-encompassing feature storage service called Fabricator, and some of the growing pains we encountered along the way. Cool. So today we're going to be talking about what caused our hypergrowth and some of the factors outside of just DoorDash pure delivery growth volume, our overall architecture, how we interact with our offline stores, and Redis with Elasticache, and some of the limits we've discovered as we've grown out to scale, and kind of what we've done with Cockroach DB as an online store afterwards. Cool. So what drove our growth on our feature store? Well, part of it was trying to make things easy. This is like a core part of our engineering culture. So a year and a half ago, we heard from our data scientists it's too hard to ship features. So we engaged in an effort to really simplify that process for them by building an all-encompassing service called Fabricator, which I'll get into later. And a big part of it that made it pretty successful is that we made it easy for data scientists to feel safe to deploy features. We added a bunch of guardrails that protect against failure and abstracted away a lot of the storage concepts for data scientists. And additionally, there was a large expansion of scope in our business around the same time. So we went into groceries, convenience, and alcohol. And a lot of this just meant that there's a lot more narrow use cases that required a machine learning model and consequently more features. And this just really ballooned how much data we needed to use. And yeah, lastly, there's been a lot of industry advancements in the last few years, and there's just so much more data available now than we had before. And then so with advent of technologies like Spark and PyTorch and distributed training, it's just become so much easier to train larger models that pretty much a data scientist's ability is just limited by their imagination and how much money you're willing to spend to train a model. Cool. Yeah, so this is kind of a brief architecture map of our service, but in general, our user really interacts with two parts of our service, Databricks and Python, and our feature registry, which is on GitHub and connects to a backend database that serves as an RPC that gives metadata to all of our other connecting services. This is the workhorse that really gives us the ability to have a fine end-to-end connection that makes things consistent across services. For the most part, our users are working in Python and PySpark on top of Databricks notebooks, in addition to some local development. We opted to use Dagster for our orchestration over the standard Airflow, just because we found that the user interface really empowers users to backfill and manage their own features, and it gives them a nice way to look at things. And it also provides a lot of manual queuing and concurrency options, in addition to tighter integrations and custom job kickoff sensors. And lastly, we also store most of our data offline on Snowflake and S3, but for the most part, we've generally opted to store things on S3 because it makes it easier to plug in another service and horizontally scale reads to that service, whereas moving directly through a Snowflake warehouse is a little bit less desirable since the scaling isn't quite as in our hands. And we have a feature service that pipelines in real time as soon as partitions are published from S3 to our online databases, which are now running on Elasticache with Redis and Cockroach DB. And to read from our DBs, we have our internal prediction service called Civil, and it reads from the feature registry so it can figure out exactly how and where to read a given feature that's called for a model. And all of our caller services really only interact with Civil prediction service. Cool. So I mentioned Fabricator real briefly. So what is it? Fabricator is our internal declarative framework that handles feature engineering, our feature registry, and our online and offline storage. It's a pretty all-encompassing internal framework, And we're not sure if it's a service, a platform, or anything like that, but it pretty much handles almost the entirety of the model development side. So this is an example of kind of how our DSL works. We generally opted to kind of make things as simple as possible. And so we tried to be flexible as well. So if you look, there's effectively two ways that a user can create features here. Either they can just input a simple SQL script and into their YAML file with whatever upstream tables they need to reference and how they want to store it, or they can, for the more advanced use cases, attach it to a Python script where we have some custom libraries where they can wrap it into a shell and a class. And what this enables us to do is manage the input and output of every data frame going in. And so we support both pandas and PySpark data frames and some other arbitrary ways to load data as well. And because we have this managed environment, we're now able to register all of the entities, the columns, and schemas are known to every other service. And with this also lets us create a pipelining service that's really simple and optimized for most every use case we have. And with just one line of code, our users can deploy their features to be available online. And all it really takes to register a feature is to just list it into a YAML file. And it will then be available to all features within a few hours or so. I mean, to all models within a few hours or so. And if you want to read more about Fabricator, there's a link below. Cool. And so a lot of our offline store just really works with one simple API call, just called get features. We've tried to make this as simple as possible, but effectively you can just list the names of all the features in a list that you want. And because we store all the entity relationships for a given feature in our registry and where they're stored, it'll just communicate with our registry and figure out how to pull all of them from S3. And in the background, we'll automatically join every entity and date as much as possible and return the minimum set of data frames based on the relationships. And because most of our offline storage is partitioned by dates or arbitrary time windows, we can join all of these automatically in the background. And we also allow options for custom joins and custom windows to retrieve, making things pretty simple to just pull. And just because everything runs on PySpark, we can just load up a ton of parquets real quickly. Cool. And now to my favorite part, talking about our journey from a single Redis cluster to using CRDB as one of our secondary backends. So for us, a lot of our guiding principles for online storage are largely reliant on availability, and resilience to failure. This is a core concern of ours because I guess maybe speculatively on my end is that on the early days of Doordash, we just really tried to focus on keeping people happy. And I think one of the outcomes when you have really bad ETAs, either due to feature store timeouts or something like that, people get really angry when they're hungry. And I've personally been angry when I've had a bad ETA prediction. It's just like, there's nothing like waiting 30 extra minutes for your food. And so part of this design is also like, just how can we have a low latency retrieval on thousands of keys in a single request? And how can we make this cost effective? So we did a few benchmarks. We've had a couple of different iterations on what feature stores we use for our backend. But for our first iteration, we settled on Redis with Elasticache. So we did a benchmark on a few different databases that we thought would be relevant and would fit our use cases. And Redis came out way ahead from the others from virtually every perspective, from a latency perspective. And CockroachDB came in a close second, but it was we just thought Redis would be a better fit for us initially. And part of why we used it is that it can scale horizontally and vertically. You can switch node types and all these things, and just the throughput is just incredible. It can read replicas and you can restore from backups, and it can support an extremely high QPS. And to this day, I think if you have a super high QPS load, there's not really an alternative that you can stack on top of it that would even be more cost effective. Cool. So our first iteration, you can see there's some sample data there where it's a sample table of a couple features and their attached entity. At first, we stored everything in a simple key value where we concatenated the entity with the feature name and just stored the value there and set an expiration for every key. And what we found is that while it performed well, there was a move to get even faster. And that was just the new challenge for our team. So we did some research, explored some other databases again, but Redis continued to win out. And we eventually ended up moving to a Redis hash map to store our features, where all the features for a given entity would be stored under a hash in Redis. And then we would set an expiration at the hash level. And this resulted in huge gains in performance and cost savings. We were able to serve features at a fraction of the cost and got huge wins as well, where I think we saw pretty ridiculous gains in overall latencies. But this ended up introducing some problems as well, and not everything was as great as it ended up being. So around the time, we just started experiencing huge growth in our platform, largely because we've made it super easy to develop features with Fabricator. We were seeing that we would need to upscale our Redis clusters pretty much every 2 weeks, and the native Elasticache functions just didn't cut it. So when you hit around 70%, 40% utilization across 100 nodes, scaling up a cluster using the native functions can take upwards of 12 to 24 hours, during which you'll experience higher latencies, drops in availability and performance. And while you can use a separate client and have some settings on your Redis client to mitigate this, it's just not ideal because you now put yourself in a state where for 24 hours, you might not be able to take any action on your cluster if there's an outage or anything like that. So we eventually invested some resources in figuring out how we can have scaling operations with no downtime. And this constituted spinning up a cluster from the last snapshot for a given one, backfilling all features, and then redirecting traffic to the new cluster. This ends up being expensive as well, because you also need to double provision your cluster for a few hours, maybe a day, for as long as it takes to get everything ready and good to go. And this also ended up being a super manual operation, since it's not something that you can automate well. So this ended up eating up a lot of our dev time. So I think after doing tons of these operations, we just figured we need to do some more. And lastly, storage is really expensive when you're storing everything on memory. Effectively, your cost will only monotonically increase, even though the number of predictions you make will not be going up as well. So secondly, hash keys are pretty expensive to create in Redis. And because we were creating many new entities with the new verticals that wouldn't be as feature dense, a lot of the cost savings we had were starting to vanish. Embeddings are also exceptionally expensive to store on Redis because one character is 1 byte, and even if you compress an embedding, some embeddings can be hundreds of characters long, making it 100 times more costly relative to a single binary feature. And next, provisioning storage predictably is pretty difficult, just because you want to have every Redis cluster in a sweet zone where it's safe enough to deploy new features, but it's also free enough where you're not just wasting money. And so sometimes you never really know when a model is going to ship. So over provisioning wasn't just really on the table there. And we experimented with having a pretty aggressive eviction behavior, so that we're not constantly uploading values that aren't being used, or they're just kind of hanging around. But this ends up being problematic, because if your upstream tables are not reliable, you can end up in a situation where you just start seeing values evict from the feature store, and you're not necessarily sure which ones are falling off, and models will drop off in performance because a subset of values are no longer being sent to the online models. And so we decided we needed to try something new and explore around some more. So that's where CockroachDB came in as our alternative. So we opted for going for a hard disk-based store. I don't think we could have squeezed out that much more performance out of Redis. So we did some research and why did we end up choosing CockroachDB? For us, it was the best performer in our last round of benchmarks. Maintenance operations on CockroachDB are virtually seamless and result in no downtime. You can, in theory, use it as a multi-region database, but I think cross-VPC data transfer rates make that a little bit less viable unless you can really figure out how to intelligently partition your data. It can automatically auto-scale and respond to skewed usage on a single node. So if data on a single node is running too hot, it'll automatically bisect and distribute the traffic until traffic is evenly balanced across the cluster. And because there are many replicas for a single range, it recovers nearly instantaneously from node failures. And the flexible indexing scheme really supports a wide variety of storage options. And lastly, it uses PostgreSQL, so it's pretty easy to onboard and kind of figure out. But that's kind of not what we ended up finding out, though. But what makes CockroachDB different is it uses this concept of ranges. So if you look at that sample table on the left, the primary key is a fake composite of, I guess, the entity key and the feature name. And primary keys are stored sequentially and chunked into ranges, where a range has the start and end value of the composite or primary key. And those ranges are then randomly distributed across nodes. There are multiple copies of a node, and there is one leaseholder that manages all the locking and distribution and managing when replicas get what. And this allows you to scale your read replicas independently from your writes as well. And then so you can also run a follower mode to have decrease the consistency, but increase the availability, making things pretty performant. And the most important part of this is that because keys are stored sequentially in ranges, that this really gives you lots of options for performance. If you're able to design your data in a structure where you're uploading and reading a bunch of values from the same range, whereas for a hash sharded index, it means that one query with maybe 100 keys will probably go to 100 different nodes if you have 100 nodes in your system. Whereas in this case, it could just go to a single node. Cool, but it wasn't all sunshine and rainbows. It was actually really hard to get this project off the ground. I think from the start of ideation to the end, we ended up taking something around like 9 months to get to a place where we're pretty happy with the performance. So yeah, I think this is something that comes with CockroachDB that's wasn't intuitive to me at the time, but I guess is obvious in hindsight. But because of the range concept, all tables start on a single node because there's only one range when you create a table. There's a bunch of ways to get around this. You can either pre-split your table into the known ranges, but this isn't as viable unless you're very confident of the distribution of your data and where it'll all go as you upload it. Or you need to slowly throttle your uploads and scale them as you go up until your table is fully saturated. And if your table isn't big enough, it may never scale out that well in the beginning unless you start manually splitting some ranges. So that graph there just shows how the CPU starts when you start uploading values to CRDB. You're effectively just maxing out one node until it splits enough times to hit every node in the cluster. Cool, and this might seem dumb, but more keys eat up more CPU. But like to elaborate on this point a little bit more, so if you kind of look at those charts there, it shows the relationship between QPS and CPU, and those actually have almost nothing to do with each other. One of the things we found out early on is that some features, like let's say a consumer-based feature where there's many more consumers than there are stores, will be spread out across more ranges. And one of the things that needs to happen during a write is that it needs to load up the range and make it ready for writing on. And so what we found is that the more ranges that are being activated during a given write, the lower the QPS would drop. And this was a significant constraint on our upload throughput. So now our main cost barrier was no longer storage or anything like that. It was actually how much compute do we need to upload all the values in a given day in a timely manner. And at this point, we're not that much cheaper per value than Redis. And this was like pretty frustrating for us just because we didn't really see this happening in the original benchmarks. And I guess everyone has an experience with this where the benchmarks rarely line up with reality and how things end up going in general. So we did a lot of optimizations here and tried to figure out the best way to get things going. And because of the sorted nature of the keys, one of the key things you can do is sort your data before uploading. Although doing a full sort in Spark is generally a bad idea because you just end up offsetting costs that would go into the online storage cluster into Spark computation costs. So you can just partially sort the partitions from S3 before uploading in like a partial sort. And then you want to batch the rows into groups, shuffle the batches so you're not hammering the same node at the same time, and then updating the entire row and not a subset. And this ends up being super important and the biggest performance gain you can get out of this. Because when you in the query plan, when you just update a subset of columns, it'll actually perform a read in the background. And in general, if you just replace the entire row, it'll get rid of that read completely, since the database doesn't really need to figure anything out at that point. Cool. And so we ended up learning some of the same lessons we learned with Redis twice. I wasn't around for the initial set of Redis changes, but given a set of two ETL tables here, you can kind of visualize what we're doing. On the left is our old format, where we had a simple composite key value, and we're just mapping a single value to a single feature and entity pair. And this ended up working okay for a bit, but it created a significantly higher number of ranges. And just because the number of writes was our biggest limiting factor, it just ended up creating too many ranges and it wasn't as performant. And we're trying to figure out how can we reduce the number of rows we need to write to get things going. So we initially opted to avoiding using the JSON map in CockroachDB, since some of the main guidelines are to have your JSON maps be less than 1 megabyte in the value column. So we're concerned that if we were to attach hundreds of features to a given entity, it would balloon that and just completely torpedo the performance of the database. But we figured out that we can eke out a lot of extra gains by grouping feature columns just to their source format or the table that they're stored in. And this way we could update multiple rows at a time for a given value and store them together and make things pretty dense, but not making them too large so as to create huge JSON maps. And this is kind of where I realized that you're always going to be making some kind of performance trade-off here, just because read performance is always going to be at odds with write performance. Fundamentally, you load a table at a time, and one table will just be a bunch of entities grouped together for a few features. But when you're calling things for reads and for creating inference in real time, what ends up happening is that you call one entity across hundreds of tables. So you've got to pay the piper somewhere. But yeah, this was actually a huge gain for us. And after we implemented this, we saw that we had a 50% improvement in our P99s or P39s, and our upload compute usage went down by something like 60 to 70%. And we're still not sure if we've saturated or gone up that high. And this is without even optimizing any of our input tables to become denser and have more rows. But overall, this was a huge win all around. And we're now at a point where we're pretty happy with the relative Redis latency trade-off, and because we're storing values at something of a fifth of the cost with these changes.
Brilliant. Brian, we're out of time. I don't know if you have anything left to present, but you can quickly wrap up very quickly.
Yeah, there's not much left, last slide, but yeah, we're looking forward. We're hoping to take advantage of indexing to create features on demand and getting really smart about our storage and upload patterns.
And there's going to be questions in the Slack, if you can jump over to the Slack, and there's a couple there I can see, and I have loads of questions, but I'll have to skip them. Thanks a million, Brian.